My name's Mark, and I'm a JavaScript engineer at a company called Kahoot. And basically today I'm going to be talking about something called building functional islands. Unfortunately, there's no, I was told that I should have added some cat GIFs or something. There's no GIFs, there's lots of code, lots of words. I've got a laser pointer, so I clearly won. To start with, I don't actually have anything to win, but just a little bit of audience participation. I'm quite keen to gauge the room, so if everyone could take stand up. And basically, I'd like everyone who knows what functional programming is to stay standing. Cool. So sorry, just to clarify, anyone that can explain the difference between functional programming and imperative or object-oriented programming, stay standing. So that worked. Stay standing if you would say you use functional programming in your JavaScript, ever. It doesn't matter how much, just a little bit. And stay standing if you would say you use functional programming for the majority of what you do. So you pretty much only write functional code. You very rarely write anything imperative. You probably don't write JavaScript. Cool. So no one who can ask too many difficult questions later. So what is functional programming? For those of you that don't know, this is going to be a really simplified explanation, much like everything in my talk. I want to try and avoid too much terminology. It's super important, but I think it can cause a lot of confusion when you're learning. I think most functional programmers would argue that you need terminology immediately. We're not going to do that. We'll see how we go. So functional programming is programming using expressions instead of statements. We're going to avoid changing any state, and we're going to avoid mutable data. It's a more declarative way of programming, and a functional programmer is going to tell the computer what they want, not how they want to get it. And before I go any further, I just want to, I don't know why I'm using that. I just want to explain statements and expressions because I realise not everyone is going to actually know what that means. So this is code using statements. It's imperative. It's in everyone's JavaScript code. Realistically, it's unavoidable. So we have assignment statements. Obviously, you're going to do this. We have control statements. Again, you might not loop like this anymore, but you're probably going to have control statements. Here we've got some mutable data, so we're pushing into an array and we're not actually assigning the return value to anything. So this is mutable data. A functional programmer is not going to be too happy with you. Whereas expressions are a combination of variables, operators, and functions, and they evaluate to produce a new value. So for people that aren't aware of what map does, it basically takes a list of data and it applies a function to each item. So what we're going to do is we're going to see this expression kind of turn into some different expressions. We're going to times 1 by 2, 2 by 2, 3 by 2, then we're going to evaluate those expressions, and it's going to be 2, 4, 6. So we've got our final value. It leaves our original array untouched. But why, I guess, is the kind of key point. Why do I want to talk about functional programming? You don't have to do functional programming. It's academic. It's potentially dry. Personally, I've seen a huge increase in FP. I'm going to say FP from now on because functional programming is really long. Concepts in front-end libraries over the past, a couple of years, I guess. And that's kind of what got me interested in it, because I was reading blogs, people were using terminology. I had no idea what they were saying. And eventually it results in me beginning to learn Haskell, which I wouldn't necessarily recommend anyone does, but it's really enlightening. You start to see the concepts and why you would want to do them. So it became quite apparent that these concepts might be really valuable for JavaScript as well. But there's not many talks about the basics. As I say, most people like to go straight into the terminology rather than starting from scratch. So that's kind of what we're going to do. We're going to look at each of the blocks to start building sort of functional code in our JavaScript. And unsurprisingly, functions are building block number 1. So there's several things about functions that we care about. So first class functions is something we care about. These are just functions. In JavaScript, all functions are first class. They're first class citizens of the language, which basically means that they can be used anywhere any other value can. So you can assign a variable to be a function. You can use a function as an argument. This shouldn't be news. In some languages, you didn't used to be able to do or still can't do this, so it's important. And they give us the ability to create higher order functions, which, again, we see these all the time. Add event listener, is a higher order function. They basically, you'll see them in event callbacks, you'll see them in array extras if you use map, filter, or reduce. But let's ignore the add event listener example because I don't feel like it's that useful. Here's my trusty add function. We're going to see a lot of this guy tonight. Basically takes two numbers, returns them added together. Then I have a function that I would never recommend writing, but it's logify. What it does is it takes a function. So you call it with a function. It's going to return a new function that is going to perform all of the logic of the original function, but it's also going to log out all the arguments you pass to the new function. So it basically works like this. You would say logify add. So we've got a new logify add function. Then we're going to call it, and you can see it logs out 1 and 2, and also logs out 3. Well, it returns 3. So it maintained all the original behavior, but we added some extra behavior. So why do we care about this? For higher order functions are functions that create new functions. They might be very similar, but they're probably customized based on the parameters that you pass to them. Or they might be functions that change other functions, a bit like my logify example, where we're decorating the function with new behavior. So we're adding the ability for it to log its params, which is kind of like a functional form of inheritance or mix-ins for functions. Obviously, if you're using classes, you could use extends. If you're using objects, you could literally mix them together. So another type of function that FP cares about is pure functions. So these functions only care about input and output. They have no side effects, so they don't know anything about the state of the application. They also don't change the state of the application. Something else about a function like add is that add is referentially transparent, and that's about as complex as the terminology you'll get. But this means that we can take an expression like this, so add 1, 2 plus add 3, 4, and we can basically just substitute the expression for its value. So we can substitute add 1, 2 with 3, and then we can substitute add 3, 4 with 7. So we're substituting the value for the eventual value of the expression, and then get 10. And our program hasn't changed. It's exactly the same as it used to be, which is why they're they're referentially transparent. And pure functions will be like that, whereas this is kind of the alternative. So no one can tell me what do something else does, so no one can tell me what add and something else does. Like, it's impossible. It's got side effects, unless for some crazy reason do something else as a no-op that does nothing. I don't know why you would do that, but it's got to read state elsewhere or mutate something else. Like, we can't do what I did a minute ago and replace the expression with the value. So we don't want code like this. Well, we need it, which I'll get onto, but what are the other benefits of pure functions? So they're testable. If you try and test a function like add, it cares about its input and output. It's very easy to test. There's no setup. You don't need to mock objects or make sure the application's in a certain state before you run your test. It's just going to work. So it's trivial to unit test, which is brilliant because testing is hard and we should be doing it. But it shouldn't be a chore. They're portable. So you can move a pure function around in your code base, you can move it between different apps. It doesn't care about where it is. So this is a brilliant thing. We can create easily reusable pieces of code. They're cacheable. Anyone that knows what memoization is, I'll explain very quickly, but it's basically if you call a function with some values and then you call it again with the same values, it's not going to actually run the code inside the function. It's just going to return the value from a cache. And pure functions let us do that. If they perform side effects, then what would you return or what would you do? You can't memoize an impure function. They're also very easy to reason about, and we hear this term a lot when we kind of go to talks about JavaScript and React usually. And this is because they're referentially transparent. It's very easy to reason about what's going on because we can just substitute things in our code. They can also be run in parallel. So if you happen to write Node and you've got different processes running at the same time, the functions don't care about the outside world, so you can run them in any order. It really doesn't matter, and that's a brilliant thing when you start writing quite complex multi-threaded code. But the reality of pure functions is that not all functions can or will be pure. You need side effects. Like, if your app has no side effects, your app's shit because it doesn't do anything. Like, if you want to read a file, if you want to make an HTTP request, if you want to handle some user input, it's a side effect. You just have to accept that, move on. Immutability is building block number 2. So as I said earlier, like functional programmers, they like to avoid mutable data. JavaScript doesn't really lend itself to this very well. So how are we going to do this? Just quickly, immutable values. If we have some data, we've got an array and we've got an object, and then we change like the first item in that array to be 2, and then we change my age to be 27. It's going to work. Like, unsurprisingly, why wouldn't it work? Some people might say, well, who cares? You can mutate objects, that's fine. Well, as we know, variables bound to objects are references, so if you mutate it in one place, it's going to mutate it everywhere. And you might want that. Like, that might be behavior you want, and your app might rely on it, but I'll be perfectly honest, you don't want to rely on that. But what can we do? So one solution is to use something called object freeze, and it was introduced in ES5. Personally, like when I first learned JavaScript and I saw this, I was kind of like, well, why would you freeze an object, meaning that you can't mutate it? I didn't really get it until I started learning about functional programming. So it's a function, object.freeze, is a function that takes some data and returns a frozen version. So we can't mutate an array item, and we can't mutate my age. Everything stays the same. But, that would be great, but if we take this complex object, complex in the sense that it has a nested object inside it, object.freeze doesn't do what you thought it did. It's actually still going to change my age, so it's not what we want. My suggestion is to use something called deep freeze. It's an npm install away, and your problem's solved. My age remains the same when I try and mutate it, and it's only 12 lines of code, unlike the potentially monolithic alternatives you might find out there. It's simply a recursive object freeze. Yeah. Why are we doing this? So we want to guarantee that values haven't changed. It's going to help us avoid mutation, and it's going to bring a sense of predictability to our code. It's also hopefully going to restore some sanity. I don't think every JavaScript developer realizes the pain mutability is going to cause them regularly. You're not going to be chasing down why objects have been mutated in different parts of your application if it's frozen. But as I say, you might want to depend on that. It's fine. So the reality of mutability is that it makes mutating objects harder. That's just a fact. If it's frozen, you can't change it. Therefore, you have to do something first to change it. So what we would do is we would clone it. And basically what we're doing is we're doing a very deep clone of an object, and this is expensive in terms of memory. Personally, I don't really care too much, which some people might say, well, you're crazy, well, you should care. If you do care, there's libraries like Mori, which implement closure, immutable data structures, and there's Immutable.js, which is a Facebook version of something similar. They don't have the same penalty to memory because of the fact that they're persistent data structures, and they basically reuse different parts of the structures, and it kind of avoids the problem. And also, not everything should be immutable necessarily. This is not a rule, it's just something that might help us. Personally, I find if you avoid mutation just by convention, it's going to make you happy. If you're not mutating like all the time, you're probably going to be a happier JavaScript developer. We've got functions, we've got immutability. What's next? Currying is what's next, and I don't know about everyone else, but when I learned JavaScript and I read about currying, I just thought, what is this thing? Like, why is it called that? And two, what's it for? I just didn't understand it. But basically what you'll find out is if you start learning about functional programming, is it's super important. In Haskell, all functions are curried. There are no uncurried functions. Bear in mind I'm just a beginner, so that might not be true, but facts. When people say things in front of you, you've got to believe them on stage. Yeah. Until you said that. So actually this next section does make more sense, I would say, in a language like Haskell, because it's like the norm. In JavaScript it's not, but I'll just explain and see how we go. So currying allows us to create functions that don't need to be called with the same amount of arguments as there are params. So we can create functions if we call, so this add, for example, again, it's back. we've got a function add, x plus y, and we're using this thing curry. This is a utility that you don't need to worry about how it works. You'll be able to get it from quite a few helper libraries. And it basically means that this function add, I can call it with only one argument, even though it takes two. And what I'm doing is creating a successor function, which basically is going to add 1 to what I give to it. So if I call it with 1, it's going to give me 2 back, which obviously, hopefully, is blowing your mind, and you believe functional programming's the right thing to do now. So please note, the function body of add, actually, this x plus y, it doesn't run until you provide all the arguments, and that can cause a bit of confusion. Like if you've put a debugger in there, for example, it's not going to run. So that caught me out a little bit when I was learning this kind of stuff. So let's use a slightly better example. Functional programming is not just all about basic mathematics. So we've got some developers. We've got 2 people in an array, and we want to get their first names. So this is quite a standard way of doing this. We're going to map over our devs, and we've got a callback function that gives us back the first prop. It gives us back the first name prop of each of the developers. This could be shortened with an array function, one-liner, which I think is quite a common kind of criticism of examples like this. But to me, it still has some issues, even if we made it shorter. So we're mentioning our dev quite a few times for no real reason. We're mentioning devs. We're coupling our code to our implementation. This is code to get first names off something. It's not code to get first names off devs. So, we could make a function that abstracts this, but the callback function, the return dev first name, for example, I would say that still doesn't really serve any purpose, except for it's essential, which is, yeah. So here's the same example using curried functions. I'm going to explain a few helpers. The grey text is a lot more visible than I realized it would be. It was meant to be really hidden. But basically, prop takes a key and an object. So it's going to take a key, then an object, and it's going to give us the value of the key of the object. So I'm currying prop with first name. So this is a function that will give me the first name of any object. And this is partially applied. I imagine that's a concept that quite a few people are aware of. If you have curried functions, you can partially apply them. That's probably not technically the super scientific version, but it makes sense to me. Map, we've also partially applied it. So we've given it a function which, as I just explained, is prop first name. And it's waiting for an array of data. This is actually unusual when you are used to using map, because map usually takes data, then a function. So the arguments might seem a little bit backwards compared even to the examples I've given in the talk, but curried functions always take their data last. And this is because it lets us create reusable functions. If we were currying with data, well, it wouldn't be reusable, but if we're currying with functions that do things, we can reuse this. And there's a really, really good talk called You're Doing It Wrong by Brian Lonsdorf that explains this much, much better. But it's an interesting thing to kind of see. And we're never, in this code, we're never saying do something with devs. We're never, well, except for here, this get first names, it's called a point-free function. It doesn't mention the data it operates on. And this is a style of programming that functional programmers are super into. They're going to strive to be point-free. They're separating the functionality from the data, which is going to aid reusability. My get first names, admittedly, is a contrived example, but I can get the first names of anything, not just devs now. So this is quite cool. So currying. It aids composition, which is actually something for the next section. And we've heard composition tonight already, which is good. The point-free style might increase reuse because it's not coupled to the implementation. We're not using unnecessary callbacks as much. I think you'd actually be quite surprised how often a curried function in a map, for example, means you don't have to have the callback whatsoever. I mean, you are kind of using one, but you're not creating these anonymous functions that serve very little purpose. The reality of currying is that if you're used to using array extras like map and filter and reduce, as in you're calling map on an array, or you're using Lodash or you're using underscore, they're not going to do the trick. You want to use something like Ramda or Lodash FP because they'll give you a curry-friendly toolkit. All of the functions in Ramda and Lodash FP, which is a functional version of Lodash, are curried by default. The parameters are flipped, so they're curry-friendly. You would get data last each time. But I'm telling you, use different tools. This might be an alien concept your team already, let alone an alien kind of library. So that needs to be considered, I would say, before you start kind of doing this kind of thing. But we're creating a smaller surface area for bugs, which I say is a win. And also, 0.3 shouldn't always be aimed for. Sometimes you just have to accept your code's not 0.3 and it might be tied to something. You don't want to make your code less readable because you're trying to be 0.3, which I think is very common in Haskell. So this kind of is what it's all been building up for. Like block 4, it's the final building block of what I'm going to go into in terms of functional programming, and it's made possible because of the other blocks. This is usually where mathematics starts appearing in functional programming quite heavily. I should talk about composition laws, associativity, and category theory, but I'm not going to talk about any of those things because it's the last talk, and I don't feel like I can explain it that well. So my explanation is going to be maths free. So what's the end result we're after when we're composing? What we want to do is we want to take a value. We want to call a function with it. So I'm calling g with my value 1. And then I want to take the result of that and call another function with it. So we're calling f with the result of calling g with our value. I'd say this is kind of an imperative approach to a very basic function composition. We'll look at the functional approach in a second, but I'd just quickly like to introduce another helper before we start getting a little bit more confusing. So we could have written the previous example like this. We get the same result. We're calling g with our value, and then we're calling f with the result of calling g with our value. And this kind of looks okay, I guess. But we could do this. So compose is another helper that you'll find in things like Lodash or Ramda. And basically it calls each function from the right to the left. So it's going to go g with the value and then f with the result of that. And it basically pipes the result of calling each function with the value from right to left, which is actually, it's exactly the same as this, the way you read it, the right to left. And so it's not very different. But let's look at a more realistic example of what I'm trying to explain. Here's some code to get a response. Well, we've got a response from a server, and we want to do a few things to it. We want to JSON parse it. We want to get the film's key value, and then we want to get the IDs of each of those films. I think that's not very easy to understand. And you would, oh no, it's got an ID. So the films basically just have an ID. That's all you need to know. So we're going to, as I say, JSON parse the response. We're going to get the films. So we're going to get the key films off of it, and then we're going to get the IDs and get an array. Now we're using real function names, not f and g. I'd say this code is not particularly pretty. I don't want to write that. I'd say it's becoming hard to read. It's becoming hard to extend. If we want to add more steps to this, if we want to add error handling to this, it's going to get really hard. So how can composition help? This is the functional version using compose. It does the same stuff. It parses the JSON. It gets the film's key off of the object using our curried prop function. And then it gets the IDs off each of those films. I've got a curried map function here with a curried prop ID. And then we're composing the whole lot. I'd say that once you're used to, I think this is quite important, once you're used to composition and once you're used to currying and once they're clear in your mind, this is easier to read. This is easier to extend, and it's more declarative. We're saying our get film IDs from response is a composition of getting the IDs off of the films prop, and then it's off of the parse JSON. We're using all of the things we've just seen. We're looking at higher order functions, pure functions. That's really important, pure, I'll explain that in a sec, and curried functions. So why would we go to all this effort? Apps should be built from lots of smaller parts. I feel like most people would agree with me there. Composition is one of those tools that we have to do this. It's very easy to refactor code that's written like this, because it's hard to show on a slide, but once you start seeing more and more composition, you can start extracting composers out into smaller functions that you might be able to reuse, and they might be point-free, so they're actually agnostic to the data they're operating on. This is going to greatly increase the reusability of your code. As with everything I've spoken about tonight, there's a reality here. It takes a while to adjust to programming like this. Also, powerful tools in the wrong hands might be dangerous. I'm sure there's some terrible, terrible code written like this out there. It requires pure functions to be sane. You can't reason about code like this if you don't know that that doesn't cause a side effect somewhere. So we want pure functions. And actually, you can compose all sorts of things. So the reality is, this is just a taster of what you could be doing. You can map and compose over things like input-output, promises, so values that aren't there yet. Error handling can be done like this as well. They're completely out of the scope of this talk, and I say I'm still learning myself, and I wouldn't necessarily suggest going that far. This isn't Haskell, and I don't think it should be. So if you're still confused about what is a functional island, not all of your code base needs to be functional. Even in Haskell, you need to make trade-offs. So even in a strict functional language, you have to have side effects. As I said, you have to do something. So how big the pure island you create is kind of up to you. You can make it as big or as small as you want. You may even have some islands you don't know about in your imperative kind of code base already. And all I'm hoping is that this is enough information that you can now see maybe you're already using functional programming concepts. And you hopefully will leave knowing how and why you might want to use it more. If you're interested in learning how to do a bit more of this, I'll put these slides up as always. And just here's some good free resources about learning this kind of stuff. Here's some really, really good paid ones. The bottom one is crazy, but really cool. And that's everything I've got. Thank you.